let's start with the Clausius statement. So this is a continuation of the Kelvin-Planck statement, and it states that it is impossible to construct a system that operates cyclically while transferring heat from a cooler to a hotter body without a net quantity of work being supplied to the system by the surrounding. Now, when you add this net quantity, you have a refrigeration system, HVAC system, your heat pump system. Now, we'll get there in a bit, but let's go through the arbitrary theory behind what a Clausius statement is and how it applies to the Carnot cycle and how it applies to the thermodynamics of a cycle where you're trying to transfer heat from a cold source to a hot source. Remember, you can transfer any amount of heat even from a cold source to a hot source, but with a net quantity of work. Now, without this net quantity, it's impossible. So the first law is not violated. It's the transfer of heat, as work is supplied to allow a low quality heat to transfer to a higher temperature reservoir. But the second law is not met. Heat will not flow by itself without extra work from cold to hot. It's not. You can't heat up your coffee in atmospheric temperatures when it cools down. So heat flows from hot to cold spontaneously. The Clausius machine, which is impossible, states that spontaneous transfer of energy, heat from a cold reservoir to a hot reservoir. It's showing that. To transfer heat from a lower to a higher temperature reservoir, we must pay a penalty. We need to do some work. We need to pay the cost of that transfer. So the Clausius and the Kelvin-Planck are effectively two sides of the same coin. They explain the second law of thermodynamics, approaching it from two different sides. If you violate the Kelvin-Planck statement, you'll violate the Clausius statement, and vice versa. It's like the laws of robotics by Asimov. So you cannot break these laws. If you break any of them, it automatically violates the other laws. You've seen iRobot, I assume, at least, if you haven't read the book. The heat engine has a thermal efficiency of 1. This is in violation of the Kelvin-Planck for this system. So you have all the heat converted to work here. So you have a heat engine. It has a 100% efficiency, and all of this heat is converted to work, being input into the refrigerator. Now, work is supplied to the refrigerator. It removes heat, QL, from a low source heat reservoir, so your lower quality heat, and transfers it to a higher temperature reservoir. So basically, you're cooling this in. You have cooling inside the refrigerator, but you need to dissipate that heat. So remember, if you have a refrigerator, it's cold inside, but behind it it's quite warm. It's because it needs to dissipate that heat somehow. So it removes the heat from the cold side, from inside the refrigerator, and throws it out. Remember, energy cannot be created or destroyed. You can transfer it, but you can't destroy it. And you reject this heat, which is the lower quality heat, plus the higher quality heat to the higher temperature reservoir. Now, check whether or not it is possible to operate a heat engine that takes heat from a hot reservoir and releases the same amount of heat to a cold reservoir but produces no work. Is this possible? First, check whether or not the cycle is consistent with the first law, and then check whether or not this cycle violates the second law. So the heat is spontaneously flowing from a high to a low temperature. Now this is just to emphasize the point. I know it's quite arbitrary and a lot of you understand it, but just so it's emphasized. No work is done by this cycle, so think of it as your hot coffee cooling down while you're drinking it. So the heat is transferred to the atmosphere, despite the fact that there's some form of insulation on your Costa coffee cup. We know this process is possible. You've seen it. You guys are seeing it at the moment. The first law may be applied to this cycle by examining the energy flows entering and leaving the working fluid. And the energy flows are absolute. These are absolute values, and their directions are indicated by the arrows. So if you see from a hot reservoir going to a cold reservoir, or your coffee cooling, your hot reservoir is your coffee, and the cool reservoir is the classroom. Starting with network equals the higher quality heat minus the lower quality heat, or the quantity of heat. For this cycle, no network is produced, so network is 0, giving QC equals QH. This heat engine, even though it's useless because it's not doing any work, does not in any way violate the first law. Energy is still conserved even if no useful work is done. So you're transferring all the energy from your coffee to this room, but you're not destroying any energy. You're just heating up this room, which is then cooled down by the HVAC system. So you need to remove that heat. You do work. That's your refrigeration part. So you're actually contributing to global warming right now. Checking the consistency with the second law is quite straightforward. This heat engine is one of the examples used to introduce the second law. So if you have 0 amount of work, the thermal efficiency of this cycle is the network over the higher energy, which equals 0. So 2 reservoirs must be larger than 0, and hence the efficiency of the Carnot cycle is TH minus TC over TH. So your higher temperature minus the lower temperature over the higher temperature, which must be greater than 0. And hence the efficiency of any real system is always lower than a Carnot cycle, which is your ideal system, 100%. Or rather, it's not 100% efficiency, but you're losing absolutely no heat. It's never 100% efficiency. So the cycle is feasible, it's spontaneous, and doesn't violate the second law because it's less efficient than the Carnot cycle. And it's a reversal, or a reversal of it's reversal. A classless machine is not possible. Yeah? So you can't reverse heat back into your coffee. The results also show that the heat transfer through a finite temperature difference is irreversible. So again, coffee's cooling down, you can't heat it up in room temperature without some kind of work input. Looking at the energy quality, you can see that the cycle transforms higher quality heat at a higher temperature to lower quality heat at a lower temperature. Now remember this higher quality and lower quality. It's your conceptual terms. Not going to come up in the exam, but the reasoning I'm saying is this way you understand what heat pumps and the refrigeration systems are. According to the quality interpretation of this second law, the cycle is feasible, it's spontaneous, and it's irreversible. So all real life processes are irreversible, as the cycle only reduces the overall energy quality. So it's irreversible when you reduce the overall quality of the energy. And the cycle is irreversible because it extracts none of the work that transferring this amount of heat is capable of doing. So the only time you can achieve this is in a perpetual machine, which again is impossible thermodynamically. So the larger difference in temperature, the more work remains unextracted. Because the more irreversible the cycle. So the larger your temperature differences, the harder it is to go back to it, because you can transfer more of this high quality energy to a lower quality energy. There's a case that has not been considered when the higher temperature equals the lower temperature. So both your reservoirs are at the same temperature. So if the efficiency is 0 and and the Carnot is now also 0. So your TH minus TC over TH equals 0. The two efficiencies are equal. Thus, for this special case, the cycle is reversible because the two temperatures are exactly the same and no work can be extracted. This is also consistent with the energy quality interpretation of the second law, as there is no change in quality and no driving force. So this in reality is absolutely impossible because you cannot go from a high temperature, or rather the same temperature, to each other because there's no heat transfer, there's no work done. So it's your absolute Carnot cycle. And the transfer of heat through an infinitesimal temperature difference is reversible. So if you assume there is an infinitesimal difference between these two temperatures, let's say you have a reservoir at 20 degrees Celsius and your hot reservoir is at 20.00000001, that's your infinitesimal. We can make an assumption that it's reversible, but again, in reality it's not. In the previous case, heat transfer through a finite temperature difference was irreversible. So if it's a finite temperature difference, so if something is cooling down, it's irreversible. But then if it has a constant temperature, then it means there is some form of work being done on it. So it's still reversible, but you have this constant temperature, unless you assume your system is something infinitesimal and the entire universe is your system. Again, like the balloon question from the first tutorial. So if the whole world is your system, then and you have your heat transfers to an infinitesimal object as opposed to the whole world, then you can assume it's reversible because the system constantly provides that heat, but still losing energy or converting energy rather. So if we consider this heat engine, it operates between a reservoir temperature of 600 K hot and 300 K. So check whether or not it's possible to operate this heat engine with the energy flows of QH, your energy flow from the hot reservoir, at 100 kilojoules per kilogram, and your work input of 60 kilojoules per kilogram. Your network output rather. So it's effectively an energy balance. Apply the first law to the cycle and check whether or not the cycle violates the second law. You guys have done energy balances, right? Yes? Okay. It's part of your process design course too. From the first law, your net work equals QH minus QC. You've seen that before. And your QC equals QH minus net work. So your QC is 100 kilojoules minus 60 kilojoules equals 40 kilojoules. That's the amount removed from or put into the colder reservoir, the lower temperature reservoir. The first law has been applied to the heat engine cycle and energy is conserved. So you have conserved this energy, but does not mean the cycle is feasible. So you know that if you remove 60 kilojoules, you'll have 40 kilojoules going into your colder reservoir rather. The simplest way of checking compliance with the second law is to use thermal efficiency. Now we know thermal efficiency is the net work over QH. So it's 60 over 100, which equals 60, or rather 60%, 0.6. And we know that the Carnot cycle, we can calculate the Carnot cycle efficiency, which is TH minus TC over TH, 600 minus 300 over 600, which is 0.5. Do you think this is feasible? Because this is larger than the Carnot cycle, but it was shown before that the highest energy efficiency, which is the highest energy efficiency possible, between any of these two heat reservoirs is a reversible cycle. This cycle clearly violates the second law because you cannot go over the efficiency of the Carnot cycle, your ideal system. So your second law effectively states that you can never work hard enough. It's like life. You can never work hard enough to achieve something, but you can get as close to it as possible. There's no such thing as perfection. Too much work is being extracted in comparison to the amount of heat being discarded to the cold reservoir. So from an energy quality perspective, there is an overall increase in the energy quality, which means the cycle is impossible. So you're increasing the overall quality of the energy, and you have more energy coming out in the form of heat. So you can't have more heat coming out than putting in, or more heat coming out than the amount of work and heat put in. Now, this might be counterintuitive when we get to the refrigeration part, so we'll get there. Consider the heat engine below. So that is, the heat engine operates between 600 and 300, and the network this time is 50 kilojoules. Is this going to be possible? So applying the first law again, we find QC equals 50 kilojoules, and checking using efficiency, we know the Carnot cycle is 0.5. So is this possible? Is this possible? Well, I'm saying it's possible as well. But basically what it means is this cycle is fully reversible because it has the same efficiency as a Carnot cycle. So it can also be concluded that the cycle is reversible. This increases and decreases energy quality balance. So with no net change. There's no net change of energy. Again, in reality, an impossible system, but your Carnot cycle is your ideal system. If we consider the same thing, but with a net work of 25 kilojoules, and apply the same law, we find that the QC is 75 kilojoules. So this time we're losing more energy. And if we check again, our efficiency will be at 25%. So this is definitely a system that is possible and more in line with reality. Now, this is the kind of system. This is basically similar to your car engine, petrol car engine. Well, they're becoming a little more efficient in this, but it's the typical car engines, 25, 29, 30% efficient, with the exception of the Mazda engines, which are significantly more efficient with petrol. So less work is being extracted in comparison to a Carnot cycle, and more heat is being discarded to the cold reservoir. So the decrease in quality when moving a large amount of heat from hot to cold reservoir is more than the increase in quality. So there's no net work is produced from heat. So you're producing this work from heat. And overall, taking both effects into account, there's a net decrease in energy quality. So you're decreasing the quality of that energy. If you think of it as having high pressure superheated steam at 500 centigrade, or low pressure, low quality steam, and this is what they call it, low quality steam at 60 degrees and let's say pressure of 0.6 bar. And the usefulness of these two types of steam are quite different. The quality is different. So you can look at it as your product and think of it as quality of that product. So in a refinery, you have your superheated steam, but sometimes because you cool it down overall, this might be useful to your process design. When you cool it down to, let's say, 60 degrees and sub-atmospheric pressure, you need to find a use for that, because still you put work in it, so it costs money. So you can change the quality by either putting work in or converting it to something useful. And the irreversibility is caused by not extracting the maximum possible work, and the cycle is capable of doing. So given these two reservoirs, so it's irreversible when you can't get the maximum possible work. And that's why there is no system in life that is reversible. So you can only have irreversibility when you are at maximum efficiency, maximum ideal efficiency. A Carnot heat engine, okay, let's go with a question. A Carnot heat engine receives 500 kilojoules of heat per cycle from a high temperature source at 652 degrees and rejects the heat to a low temperature sink at 30 degrees. What is the thermal efficiency of the Carnot engine? I'll let you actually calculate that.